Here we're going to look at Born-Haber cycles, how to construct a Born-Haber cycle and calculations involving Born-Haber cycles. Now, before you watch this video, you really should have a good grasp on the definitions and the equations of all the enthalpy changes involved in Born-Haber cycles. If you don't, then you're going to struggle to understand what's in this video. So you have to know the definitions, be able to write equations for all the enthalpy changes in a Born-Haber cycle. Now, Born-Haber cycles are useful as they allow us to work out these things called lattice formation or lattice dissociation enthalpies, and that gives us an idea on the strength of the ionic bonding in an ionic compound. So here I've written down the equation for the lattice formation enthalpy of sodium chloride. And we can link this if we write the elements, sodium and chlorine underneath, and this here, this enthalpy change, you should be able to recognise as the enthalpy of formation. Now, how we get from the elements to the gaseous ions, which I'm just going to call this enthalpy change delta Hx, this delta Hx is a series of different enthalpy changes, and we can show these enthalpy changes in a Born-Haber cycle. So we've got in effect here something very similar to a Hess cycle, but by showing these enthalpy changes, we are going to construct a Born-Haber cycle. Now, first thing I'm going to do is I'm going to draw a line there. That represents energy, so it's like a y-axis of energy. And when drawing these Born-Haber cycles, the first thing I'm going to do is I'm going to write down the energy level of the elements. So the sodium solid plus half chlorine gas. It's the first thing you need to do. Then I'm going to write down the energy of the ionic compound. Now, in this case, that is NaCl solid, and this enthalpy change represents the enthalpy of formation. So, in effect, I've already done this part of the Hess cycle in my Born-Haber cycle. What I need to do now is get from here to here, get from the elements to the gaseous ions, and that involves a series of different enthalpy changes. So what I'm going to do first, I'm going to try and get the sodium, solid sodium, into gaseous sodium ions. The first thing I need to do is I need to atomize the sodium. Now, any arrow that goes up, should have said this earlier, represents an endothermic process. So the enthalpy of formation is nearly always an exothermic process. So the arrow there is going down. So what I'm going to get here is I'm going from sodium solid to the sodium ions. In effect, I'm breaking this giant metallic lattice into gaseous sodium atoms. And that there is delta HAT for sodium, the enthalpy of atomization of sodium, forming 1 mole of gaseous atoms. I then need to ionize the sodium. I'm going to convert it into sodium ions. And again, we need to balance it by adding an electron. And that is the first ionization energy of sodium. So that's delta H 1 IE for sodium. So I've got the sodium where I need it to be. I've got from sodium solid to gaseous sodium ions. I now need to concentrate on the chlorine. And again, we're going to atomize the chlorine, convert the chlorine molecules into chlorine atoms. And again, that's an endothermic process. We need to put energy in. Oh, we've converted into chlorine atoms now, so it becomes Cl gas. And that there is my enthalpy of atomization of chlorine. Now, the next enthalpy change is actually an exothermic one, so I need to do an arrow going down, and I'm going from sodium chlorine atoms, to chloride ions. That's an exothermic change. There's a net attraction, and the chlorine atoms and the electrons, the nucleus of the chlorine atom and the electrons, a net attraction, so it's an exothermic process. So that there is my delta H first electron affinity for chlorine. And we can see now that this here then is my lattice formation enthalpy. Going from the gaseous ions, as we can just go back up there, we're going from our gaseous ions to the solid ionic compound is lattice formation enthalpy. Now, if you've given, you can work out any one of these enthalpy changes if all the others are given. Now, in this particular example, I'm going to work out the lattice formation enthalpy. All the other ones will be given. The lattice formation, the enthalpy formation, of sodium chloride is equal to minus 411. The atomization enthalpy of sodium is plus 109. First ionization energy of sodium is plus 494. The enthalpy of atomization of chlorine is plus 121. And the first electron affinity of chlorine is minus 364. So in effect, this is what I want to work out. Now, again, based on Hess's law, we're saying that this enthalpy change here is the same as going from here to here. The enthalpy change is independent of the route taken. So it's the same as going from here to here. Now, the key here is that any arrow going the opposite way to this one here, this red arrow, the sign changes. So I want to go from here to here. So let's see. The first then, I'm going from here to here. The minus 364, the arrow's going the wrong way, so I change that now to plus 364. Again, let's have a look at my arrow. The enthalpy of atomization of chlorine arrow is going the wrong way, so I change that from plus 121 to minus 121. Again, that's my arrow. My ionization energy of sodium is going the wrong way, so that comes minus 494. Again, this is my arrow. Remember, it's base of the arrow, the two heads of the arrow should meet. My atomization of sodium is going the wrong way. That becomes then minus 109. Again, let's have a look. Oh, my enthalpy of formation, the arrow is going the same way as the big red one, so the sign stays the same, so that stays as minus 411. And that then is how I'd work out my lattice formation enthalpy, and when I do that calculation you get an answer of minus 771. All these values are in kilojoules per mole, so that's my answer. I'm going to have a look at another Born-Haber cycle now, and this time we're going to look at calculating the I'm going to work out something different. I'm going to work out the second ionization energy of magnesium. I'm going to do it for magnesium chloride, MgCl2. So again, let's draw my axis energy. So what's the first thing that we do? The first thing we do is we draw the elements. So I draw now, it's magnesium chloride, MgCl2, so it's Mg solid plus Cl2 gas. Next thing is to draw the solid ionic compound, MgCl2. And again, this enthalpy change here is my enthalpy of formation of magnesium chloride. So again, now I want to get from magnesium solid to gaseous magnesium ions. First step again is I need to atomize magnesium. So I'll convert the magnesium solid into magnesium atoms, gaseous magnesium atoms. So that represents the enthalpy of atomization of magnesium. I then need to ionize it. So I need to convert this into magnesium ions. Again, plus an electron. And that there is my first ionization energy of magnesium. So delta H, first ionization energy of magnesium. Remember that magnesium, when we form MgCl2, forms magnesium 2 plus ion, so I need a second ionization energy. So I'm now going to form an Mg2 plus ion. Plus 2 electrons. I'm now going to atomize. I've got the magnesium where I need it to be. I'm now going to atomize my chlorine, convert the chlorine molecules into chlorine atoms. I need to put the state symbols in. Cannot ever forget the state symbols. And that there represents my enthalpy of atomization of chlorine. So again, we need to go down because we've got an exothermic process where the chlorine atoms become chloride ions. That there represents my first electron affinity for chlorine. And then you've got your lattice formation enthalpy. Now, this time, we're going to work out the second ionization of magnesium. That's what we've been asked for. And all the other values will be given. Now, the enthalpy formation of magnesium chloride is minus 643. The enthalpy of atomization of magnesium is plus 150. First ionization energy of magnesium is plus 736. That's what I want to work out this time. The atomization of chlorine. Now, you may be given the table as 1, 2, 1. You've got to remember that the enthalpy of atomization is for the formation of 1 mole of atoms. Now, we formed 2 moles of atoms there, so it would be 2 times 1, 2, 1, which is plus 242. So remember, the enthalpy of atomization is the formation of 1 mole of atoms. So this here will be double the enthalpy of atomization. The electron affinity is minus 364. But again, that's for the formation of 1 mole of gaseous negative ions. And we form 2 moles of gaseous negative ions. So you need to multiply that by 2 to give you minus 728. Lattice formation of magnesium chloride is minus 2493. So I need to work out this second ionization energy of magnesium. In effect, I need to go here. It's the same as going from there to there. Base of the arrows and the heads of the arrows should meet. Remember, any arrow going the wrong way, you change the sign. So the first thing we do is the 736. Well, that's going the wrong way, so we change that to minus 736. Let's just show you the arrow again to show you why. That's the arrow. You can see the 736 arrow is going the wrong way. The 150, well, that's again going the wrong way. That's changes to a minus. If we look at this arrow again, the 643 minus 643, well, that's going the same way, so that sign stays the same, and that stays as a minus 643. The LFE, the minus 2493, let's have a look. Well, that is going the wrong way. So we change that to a plus. That becomes plus 2493. The electron affinity, let's have a look again. Well, that is going the wrong way as well. So that becomes plus 728. And let's take the last. Again, the atomization of chlorine arrow is going the wrong way. So that becomes minus 242. So when we do that calculation, that would give us the second ionization energy of magnesium. Now, it's very important to note that you should be able to guesstimate what that second ionization energy is. You know it's going to be positive, and it's going to be significantly more positive than this. It's going to require more energy to remove the second electron from magnesium compared to the first. And if you do that sum, you end up with plus 1450 kilojoules per mole. So that gives you a sensible answer. It's got to be more positive than the first ionization energy enthalpy. So you've got two Born-Haber cycles there, one for working out the lattice formation enthalpy of sodium chloride, and one is for working out the second ionization energy of magnesium, and you might be required to work out any of these enthalpy changes given all the others. I'm just going to make a little comment on the thing that affects the magnitude of these lattice formation enthalpies. Now consider the following four ionic compounds. The lattice formation enthalpy of sodium chloride, we've worked out 771, minus 771. Potassium chloride is minus 711. We've already said that magnesium chloride is minus 2493 and barium chloride is minus 2049. And I'm hoping we can see by looking at this table what factors affect the magnitude of this lattice formation enthalpy. We can see in both cases, here we've got a group 1 metal ions, and here we've got group 2 metal ions. And you can see that there's a massive increase in the magnitude of this negative value going from 1 plus ions to 2 plus ions. So we would say, as the charge on the ion increases, the delta H LFE, this is really important now, the quality of language becomes more negative. Please don't say gets bigger. You've got to say becomes more negative or becomes more exothermic. We can also see, now if we look at sodium and potassium, both got the same charge. Potassium is a bigger ion, and the LFE becomes less negative. Again, magnesium and barium, same charge. Barium is a bigger ion, the LFE becomes less negative. So we can also say, as the size of the ion gets smaller, again the lattice formation becomes more negative. So a high lattice formation enthalpy is favoured by small, highly charged ions, and that's the same whether it's a negative ion or a positive ion. So now you've seen that, you should be confident that you can work out any of these values within a Born-Haber cycle.